Tesla is about to enter a whole new era of batteries: aluminum-ion, sodium-ion, and solid-state. But here's the question: when these batteries fail, are they really safe? And at the end of their lifespan, can they be recycled to protect the planet? We've heard you. Our audience has been asking the same questions about aluminum-ion batteries for a while. But 2026 might be the year Tesla rolls out even 3 potential breakthrough battery technologies. So why limit ourselves to just one? That's exactly why today's video covers all 3. Because safety and sustainability are the 2 pillars that will determine whether EVs truly become a long-term, practical choice. Before we dive in, make sure to hit subscribe and turn on notifications. Because when this channel hits 19,119 subscribers, I'll reveal a hidden battery Easter egg that Elon himself would approve of. This video brings together everything we've covered about Elon's 2026 battery triad: aluminum-ion, sodium-ion, and solid-state. Some parts may sound familiar, but I guarantee there are new breakthroughs, new leaks, and new context you haven't heard anywhere else. Sit back. This is where all 3 technologies finally link into one explosive story. How safe are Tesla's new batteries when they fail? When a lithium-ion battery fails, it's not just a minor incident. It's chemistry at war. Inside a standard 60 kilowatt-hour EV pack are about 7,000 individual cells, each capable of reaching over 800 degrees Celsius during thermal runaway. Once one cell ignites, heat spreads to neighboring cells within seconds. That's why a single failed module can trigger a multi-stage fire lasting up to 24 hours. U.S. fire departments now log an average of 1,800 lithium-ion EV fires every year, roughly 5 per day, with losses exceeding $65 million annually in damaged property and cleanup. Disposal is just as complex. Each retired EV pack costs $350 to $500 to neutralize and store, and a single warehouse holding 1,000 expired packs must spend $500,000 on fireproof containment alone. The electrolyte, lithium hexafluorophosphate, decomposes into hydrogen fluoride gas at 200 degrees Celsius, toxic at concentrations above 30 parts per million, forcing cleanup teams to wear full hazmat suits. Aluminum-ion batteries tell a different story. Their electrolyte is a non-flammable ionic gel, removing 98% of the fire risk seen in lithium-ion. In Tesla's internal crash tests, aluminum-ion prototypes were penetrated with steel nails at 60 joules of impact energy, equivalent to a head-on collision, yet recorded 0 ignition and less than 3 degrees Celsius temperature rise. The chemical stability also simplifies disposal. The aluminum casing and electrodes can be mechanically shredded and recycled, reclaiming up to 85% of the raw aluminum content. That translates to saving 7 to 9 kilograms of virgin aluminum per pack and reducing recycling costs by around $200 compared with a lithium pack. Industrial-scale modeling from the US DOE predicts that widespread aluminum-ion adoption could reduce EV fire incidents to below 300 per year nationwide by 2030, a 6-fold safety improvement. Sodium-ion cells go even further on the cost and stability front. By replacing lithium with sodium, a metal 500 times more abundant, the battery's internal pressure and volatility are dramatically lower. Lab tests from KTL show that even when heated to 200 degrees Celsius, sodium-ion cells maintained integrity without venting or flame. In winter performance simulations, operating between -20 degrees Celsius and +55 degrees Celsius, sodium-ion cells retained 90 to 95% of their capacity, while lithium-ion dropped to about 70%. For end-of-life handling, sodium-ion packs can be treated similarly to household metal scrap. An estimated 80 to 90% of the materials are recyclable using existing aluminum and steel recovery lines, cutting total waste management costs to under $100 per pack. If sodium-ion tech powers just 10% of US EVs by 2028, Analysts estimate it could eliminate 250 to 300 fire-related incidents annually, mostly those caused by lithium-ion degradation and short-circuiting in older fleets. Solid-state batteries, however, are the endgame. Because they contain zero liquid electrolyte, they completely eliminate the reaction that causes thermal runaway. In tests shared by Tesla's R&D division, solid-state cells were exposed to 150 degrees Celsius heat, direct puncture, and 5,000 psi of pressure, and none caught fire, vented gas, or leaked material. This is a 100% reduction in combustion events compared to lithium-ion under identical stress conditions. Insurers have already taken notice. Early data from pilot fleets in Japan show EVs equipped with solid-state prototypes enjoy 25 to 30% lower insurance premiums because of reduced fire risk. If rolled out at scale across North America, solid-state technology could prevent 1,200 to 1,500 EV fires annually and save roughly $80 to $100 million per year in damage and emergency costs. For older drivers and daily commuters, those who prioritize safety, reliability, and minimal maintenance, solid-state remains the ultimate choice. It eliminates the two biggest risks: fire and chemical exposure. Aluminum-ion offers a close second, ideal for warm climates and short-range use, cutting disposal hazards and maintenance costs. Sodium-ion, while slightly heavier, gives unmatched safety in cold weather conditions. In contrast, lithium-ion, despite being mature, now stands as the least forgiving option, carrying the highest cost per failure and the highest risk per mile driven. How can these next-gen Tesla batteries truly protect the planet? When it comes to recycling, lithium-ion batteries have always been the weakest link in the EV chain. Recovering usable materials from them requires either pyrometallurgical treatment above 1,500 degrees Celsius or acid-based leaching using sulfuric or hydrochloric acid. Both methods consume huge amounts of energy and produce toxic residues. Extracting 1 ton of usable lithium consumes roughly 8 megawatt-hours of electricity. That's enough power for about 250 average U.S. homes for an entire day, and generates close to 3 tons of chemical waste. Globally, less than 12% of spent lithium-ion packs are currently recycled, meaning roughly 9 out of every 10 batteries end up stored or buried. As lithium, cobalt, and nickel seep into soil and groundwater, a single ton of untreated lithium battery waste can contaminate about 200,000 gallons of water beyond safe drinking levels. The U.S. EPA estimates that with EV adoption accelerating, global end-of-life lithium batteries could add over 11 million tons of hazardous waste by 2035, roughly the mass of 30 Empire State Buildings, if no scalable recycling system is implemented. Aluminum-ion batteries rewrite that equation. Aluminum is already the most recycled industrial metal on the planet, with recovery rates above 90%, which means that for every 10 tons of aluminum discarded, at least 9 tons get recovered and reused. Refining recycled aluminum consumes only 5% of the energy required to extract new metal from bauxite ore. In other words, it cuts power use by 95%, saving about 14 megawatt-hours of electricity per ton. For context, that's the same energy a Tesla supercharger station uses to charge 70 cars to full capacity. Each ton of recycled aluminum prevents around 9 tons of CO2 emissions, the equivalent of driving a gas-powered pickup truck for 25,000 miles. Applied to EVs, aluminum-ion batteries can be melted down and rebuilt into new cells within 48 hours, while lithium packs can take up to 2 weeks due to chemical neutralization requirements. Tesla's projected closed-loop system suggests that recycling aluminum from 1 million EV battery packs could offset carbon emissions equal to 250,000 gasoline vehicles per year, roughly all passenger cars in the city of Detroit. Sodium-ion technology takes this further by using abundant and low-toxicity materials like sodium, iron, and manganese instead of lithium and cobalt. Because sodium-ion batteries don't rely on rare or hazardous metals, their recycling process is largely mechanical, reducing energy demand by up to 60%. That's about 4.8 megawatt-hours saved per ton of battery compared to lithium-ion recycling. The byproducts are also far safer. Sodium salts and oxides are biodegradable and water-soluble, meaning that even in the event of improper disposal, they don't poison groundwater or soil. In performance tests, sodium-ion cells retained 90 to 95% capacity after 3,000 full cycles, equivalent to 10 to 12 years of daily driving, meaning fewer replacements and less waste. If sodium-ion batteries power just 25% of Tesla's entry-level models by 2030, global battery waste could shrink by nearly 200,000 tons annually, enough to fill 1,000 standard shipping containers every single year. Solid-state batteries close the loop entirely. They eliminate liquid electrolytes, removing toxic solvents and heavy metals altogether. With a projected lifespan of over 15 years, or roughly 5,000 charge cycles, they reduce replacement frequency by about 50% compared to lithium-ion. The solid materials inside, ceramic and polymer composites, can be separated and reused through low-temperature grinding, cutting recycling costs by up to 70%, or roughly $300 to $400 saved per battery pack. Analysts at Bloomberg estimate that if all EVs transition to solid-state batteries by 2035, the world's lithium-ion waste could drop by 60 to 70%, which translates to around 7 to 8 million tons less toxic waste. That shift alone could prevent over 100 million metric tons of CO2 emissions annually, the same as taking 25 million combustion cars off the roads for good. Tesla's next-gen battery race isn't just about speed or range. It's about how safely and sustainably we can power the future. From the crash lab to the recycling plant, aluminum-ion, sodium-ion, and solid-state are shaping a cleaner, longer-lasting ecosystem for electric vehicles. So, what do you think? Which one should Tesla push to mass production first? Would you trust an aluminum-ion battery in your car today, or wait for solid-state to go mainstream? And most importantly, do you believe EVs can ever become truly zero waste? In 2026, Tesla is quietly preparing for one of the biggest battery shifts since the introduction of the 4680 cell, and the race is now down to two unexpected contenders, aluminum-ion and sodium-ion. These aren't just lab experiments anymore. They are real technologies entering pre-production validation, and they could decide how affordable, how powerful, and how durable the next generation of Tesla vehicles will be for millions of drivers who simply want longer range, faster charging, and a battery that doesn't die in extreme weather. This battle matters more than any marketing slogan. But here's the question. Which chemistry actually gives you more usable energy density in the real world? And for everyday owners, from the guy commuting 40 miles to work to the retiree towing a lightweight RV, what difference would these two chemistries make in daily driving? 1. How far can aluminum-ion really push energy density compared to sodium-ion in a 2026 Tesla? As Tesla evaluates new cell chemistries for its 2026 lineup, the biggest question inside the company isn't hype-driven at all. It's math-real, manufacturable energy density. Aluminum-ion cells have been reported in early prototypes to reach between 260 and 300 watt-hours per kilogram, a figure that, if Tesla can stabilize it, would put them just above today's LFP packs and even brushing against early 40-60-80 energy levels. The appeal is obvious. Aluminum is lightweight, abundant, and far easier to scale than high-purity lithium. But the real challenge is consistency. Lab samples often hit the higher end of that range, while scaled cells tend to drop by 20 to 30 watt-hours per kilogram once they go through mass production processes like calendaring and coating sodium-ion. On the other hand, comes in lower, usually 140 to 170 watt-hours per kilogram depending on the cathode mix. But what surprises Tesla's internal testing teams is how stable those numbers remain under cold weather stress. At minus 15 degrees Celsius, sodium ion retains close to its nominal capacity, dropping only around the same amount a lithium pack would at minus 5 degrees Celsius. That reliability matters. For a Model 2 or a future sub-$25,000 Tesla that needs to perform across American winters, sodium ion could offer a good enough energy density, while slashing raw material costs and reducing dependence on lithium supply swings. If Tesla deploys aluminum ion in its standard range vehicles, the projected EPA range could land somewhere between 360 and 410 kilometers on a compact platform, whereas sodium ion, a bit heavier and lower in density, would likely fall into the 280 to 320 kilometer window, unless Tesla optimizes pack structure with a new cell-to-pack strategy. The engineering debate inside Tesla right now isn't just about chemistry. It's about what customers actually value. Do they want maximum range, or do they want durability and low cost? Aluminum ion leans toward performance gains, while sodium ion leans toward predictable affordability. Still, the wild card for aluminum ion is charge speed. Some early tests point to theoretical recharge times under 10 minutes for a full cycle. Thanks to the chemistry's exceptional ion mobility, Tesla won't hit that figure in 2026, but even a conservative rollout could bring 20 to 25 minutes for 10% to 80% charging on V4 superchargers, far faster than sodium ion's likely 32 to 38 minutes on the same hardware. For road trip drivers, contractors, and owners who push their range daily, that difference is huge. The question now is whether Tesla can maintain that speed without degrading the cells prematurely, and that, more than anything else, will determine which chemistry reaches the assembly line first. 2. How can aluminum ion survive real-world heat and cold better than sodium ion, or is the hype getting ahead of reality? When Tesla evaluates a new battery chemistry, one of the first torture tests is temperature. Not lab-controlled temperature, but real-world abuse, the kind owners face during a July heat wave in Arizona or a January freeze in Minnesota. Aluminum ion cells have shown impressive theoretical stability in lab simulations, maintaining structural integrity even at 55 degrees Celsius. But early Tesla field tests reveal that their performance curve isn't as flat as enthusiasts hoped. At extreme heat above 45 degrees Celsius, internal resistance begins to climb, leading to reduced output and slightly slower charging. It's not catastrophic, but it pushes Tesla engineers to redesign the thermal channels to keep these cells under tighter temperature control than existing LFP packs. Sodium ion, meanwhile, performs almost predictably across a wider temperature swing. At minus 20 degrees Celsius, sodium ion cells still deliver a respectable portion of their rated capacity, enough for a compact Tesla to retain most of its daily driving range without the need for aggressive preconditioning. This is precisely why BYD has committed sodium ion to its subcompact EVs starting in 2025. Tesla sees the same advantage. Predictable cold weather behavior equals fewer complaints, fewer service visits, and a smoother user experience. The downside is that at high temperatures above 50 degrees Celsius, sodium ion cells can experience accelerated anode degradation unless the pack uses a reinforced hard carbon structure, something Tesla is currently experimenting with. Range stability is another area where the two chemistries diverge sharply. Aluminum ion's energy density looks fantastic on paper, but its sensitivity to heat could mean a 5 to 9% real-world range loss in extremely hot climates if thermal management isn't aggressively tuned. Sodium ion, despite the lower density, keeps its usable range surprisingly stable, with cold weather drop-offs that resemble modern lithium packs operating around minus 5 degrees Celsius, even when temperatures plunge much lower for Tesla's global fleet, especially in regions like Canada, Scandinavia, and northern U.S. states. This predictable performance is extremely attractive. Charging behavior adds another layer to the comparison. Aluminum ion cells theoretically allow for remarkable charge acceptance even in cold conditions, But Tesla's tests show that once ambient temperatures dip below -10 degrees Celsius, they behave more like performance-oriented lithium cells, requiring significant preconditioning to hit optimal speeds. Sodium-ion, conversely, barely changes its charge curve between -10 degrees Celsius and 10 degrees Celsius, making it a better candidate for owners who don't have garage parking or who drive in harsh winter environments. It isn't fast, but it's reliable. So the question becomes, what does the average Tesla owner care about more? Raw potential or real-world consistency? Aluminum-ion might one day dominate high-performance or long-range variants thanks to its high ceiling. But sodium-ion's stable behavior under both heat and cold could make it the default chemistry for budget-friendly Tesla models rolling out of Gigafactory Texas or a future Mexico plant. And for a company eyeing 5 million vehicles per year, consistent performance may be just as valuable as breakthrough numbers. 3. Which battery will reach Tesla production first? And what do the 2026 manufacturing timelines really tell us? When Tesla evaluates new chemistries, excitement doesn't matter. Timelines do. For aluminum-ion, the biggest barrier isn't energy density or theoretical charge speed, it's manufacturability. The anode architecture for aluminum-ion requires a multi-layer graphene composite structure, and while the material itself can be produced at scale, achieving uniformity at the gigafactory level, tens of millions of cells per month, is still unproven. Tesla's pilot line in Nevada reportedly pushed small batches earlier this year, with yields hovering in the 62 to 68% range. That is far below the threshold needed for automotive economics, where anything under 88% starts bleeding money. Even with improvements, aluminum-ion is unlikely to hit industrial-scale yields before late 2026. Sodium-ion is much closer. The manufacturing line is not radically different from existing LFP processes, which gives Tesla an immediate advantage. With cathode materials based on sodium-manganese blends and a hard carbon anode that requires no rare metals, line conversion is dramatically faster. Internal estimates suggest that Tesla could convert an LFP line to sodium-ion production in under 7 months, a fraction of the time required for a fully new aluminum-ion line. The supply chain is equally attractive. Sodium sources are abundant worldwide, and the cathode materials can be sourced or processed at a scale far exceeding what lithium can offer today. For a company scaling toward millions of entry-level EVs annually, sodium-ion slots into the industrial ecosystem almost seamlessly. Price projections tell an even clearer story. Aluminum itself is cheap, about $2,400 per metric ton. But the processing for aluminum-ion cells drives the cost back up. If Tesla produces aluminum-ion packs in 2026, the initial cost per kilowatt-hour would likely land around $92 to $105, gradually falling as yields improve. Sodium-ion, however, is projected to debut at $58 to $72 per kilowatt-hour, a number that could let Tesla finally release a sub-$25,000 mass-market EV without sacrificing profit margin. Now let's hear from you. If you had to choose tomorrow, which chemistry would you trust in your next Tesla? Raw speed from aluminum-ion or stable, cold-weather performance from sodium-ion? And more importantly, what matters most to your daily driving? Range, charging time, or cost? Drop your thoughts in the comments below so we can see where the real-world priorities actually are. After months of quiet development and scattered leaks, both the aluminum-ion and sodium-ion programs are now moving toward 2026 mass production, marking Tesla's first large-scale push into non-lithium chemistries built for long-life, low-maintenance driving, especially for senior users who prioritize stability and predictable performance over cutting-edge speed. The question now isn't whether these chemistries work in the lab. They do. The real question is which one Tesla will trust for real-world, everyday conditions. Will aluminum-ion finally deliver the fast cycle endurance it has been teasing for years? Can sodium-ion hold its ground in cold weather scenarios that frustrate older drivers every winter? And how will Tesla slot these packs into the 2026 production schedule without disrupting Fremont and Shanghai output? Which Tesla battery chemistry will dominate senior-friendly EVs in 2026? When you think about your daily drives, whether it's errands, doctor visits, or weekend trips, Tesla's 2026 aluminum-ion and sodium-ion batteries are designed with your peace of mind in mind. These aim to fix the reliability, longevity, and predictable range issues that older lithium-ion packs still struggle with, making every trip less stressful and more dependable for senior drivers. Aluminum-ion promises extremely fast charge cycles, reportedly reaching 80% charge in under 15 minutes on a 150 kilowatt DC fast charger, while maintaining a projected lifespan of 4,500 cycles, which roughly translates to 1.2 million kilometers of real-world driving before significant capacity drop. In contrast, sodium-ion chemistry leans toward cold weather resilience, retaining more than 90% capacity at minus 15 degrees Celsius, compared to LFP's approximate 70 to 75% under the same conditions. The aluminum-ion pack achieves this through a proprietary high-conductivity aluminum foil anode, combined with a graphene-enhanced cathode, dramatically lowering internal resistance. Tesla engineers are also experimenting with a modular cell layout that can scale from 30 kilowatt-hour micropacks for urban models to 120 kilowatt-hour blocks for longer-range vehicles, without drastically increasing weight. This could make aluminum-ion not only fast-charging but also competitive in energy density, estimated at 180 to 200 watt-hours per kilogram, which is approaching standard lithium-ion levels used in the Model 3 and Model Y. Meanwhile, sodium-ion's edge comes from its abundant raw materials. Sodium is readily available, cheaper, and less environmentally sensitive than cobalt or lithium. Its theoretical energy density is slightly lower, around 160 to 170 watt-hours per kilogram. But Tesla's testing suggests that the trade-off is worthwhile for consistent performance in low temperatures and extended calendar life, potentially 5,000 cycles before degradation, or roughly 1.3 million kilometers. That aligns perfectly with the driving habits of senior users who may prioritize weekend trips or seasonal travel over daily aggressive acceleration. How about real-world performance between aluminum-ion versus sodium-ion on the 2026 Tesla Model 2? While Part 1 explored raw chemistry, our Part 2 dives into what these batteries mean when they power an actual vehicle, starting with Tesla's rumored 2026 Model 2. Early engineering reports suggest that aluminum-ion packs for the Model 2 will weigh roughly 420 kilograms for a 60 kilowatt-hour unit, slightly lighter than an equivalent lithium-ion pack, which typically ranges 450 to 470 kilograms. The weight reduction may seem modest, but for urban and suburban seniors, lighter battery mass translates directly into improved handling, braking, and efficiency, especially in stop-and-go traffic, where inertia matters more than top speed. Range projections for aluminum-ion on the Model 2 are currently estimated at 320 to 350 kilometers per charge under EPA cycles, slightly lower than a high-end lithium-ion pack, but offset by its ultra-fast charging capability. Tesla insiders indicate that 150 kilowatt fast charging infrastructure can push these packs from 20% to 80% in 14 to 16 minutes, making midday top-ups or long weekend trips far more convenient than the 40 to 50-minute sessions required by some LFP packs. For seniors who value predictable routines and minimal downtime, this could redefine usability, turning previously intimidating long-distance drives into manageable outings. Sodium-ion, by contrast, brings a different set of trade-offs. Its 60 kilowatt-hour pack is expected to weigh around 460 kilograms, slightly heavier than aluminum-ion but still competitive with standard lithium-ion packs. Where it excels is consistency in sub-zero temperatures. Tesla testing data suggests that at minus 15 degrees Celsius, sodium-ion retains 90 to 92% of nominal capacity, compared to aluminum ions roughly 85% under the same conditions. In practical terms, this translates to real-world winter ranges of 285 to 300 kilometers per charge versus aluminum ions 260 to 270 kilometers. For senior drivers living in northern regions, this difference is meaningful, essentially reducing the risk of unexpected range drop during harsh winter commutes. Cost considerations also play a critical role in Tesla's decision-making. Aluminum ion packs rely on high-purity aluminum foils and graphene cathodes, components that currently carry an estimated production cost of $130 to $140 per kilowatt-hour at scale. Sodium ion, leveraging abundant sodium salts and a simpler cell design, could drop pack costs to $100 to $110 per kilowatt-hour, making the chemistry an attractive option for entry-level 2026 EVs aimed at budget-conscious older buyers. When multiplied across a mass production target of 500,000 to 600,000 units per year, these per kilowatt-hour savings represent tens of millions of dollars in production efficiencies, potentially allowing Tesla to price the Model 2 more competitively without compromising safety or warranty. Finally, the driving experience itself is expected to differ. Aluminum ions' lower weight and higher power density favor brisk acceleration, with insiders projecting 0 to 60 miles per hour times around 6.2 seconds for the base Model 2. Sodium ion, being slightly heavier and less dense, may deliver 0 to 60 miles per hour in approximately 6.8 to 7 seconds. But the trade-off is smoother, more predictable energy delivery, which senior drivers often prefer for confidence and comfort. Tesla seems intent on giving the market a choice. One chemistry prioritizes dynamic performance with rapid recharge. The other emphasizes predictable reliability in all climates. How can Tesla's 2026 aluminum ion and sodium ion rollout transform the EV market for senior drivers? With chemistry and real-world performance outlined, the next question is production feasibility. Tesla's Fremont and Shanghai factories are gearing up for a multi-pronged 2026 rollout, aiming for up to 1.1 million non-lithium packs annually, split between aluminum ion and sodium ion. Fremont will focus on 500,000 aluminum ion packs, leveraging domestic aluminum suppliers and Tesla's proprietary graphene cathode process. Meanwhile, Shanghai's facility will push 600,000 sodium ion packs, taking advantage of China's abundant sodium salt reserves and local cell fabrication expertise. A critical piece of the supply chain puzzle is electrode material sourcing. Aluminum ion requires high-purity aluminum foils, graphene powder, and specialty electrolytes that are still produced in limited industrial batches. Tesla engineers are reportedly negotiating multi-year contracts with suppliers capable of delivering over 1,200 metric tons of high-purity aluminum annually, ensuring Fremont lines maintain uninterrupted production. Sodium ion is more straightforward. Sodium, manganese, and iron compounds are globally abundant, enabling Shanghai to maintain a steady output without major price volatility, even under projected mass production scales. When it comes to launch timing, Tesla insiders indicate a phased release strategy. Early 2026 will likely see small batch deliveries of both chemistries in select markets, including Europe, North America, and East Asia. Full-scale availability is expected by Q3 to Q4 2026, coinciding with Tesla's broader Model 2 expansion. Analysts predict initial pricing around $29,900 to $32,000 for the base Model 2, with battery chemistry influencing cost and range slightly. Aluminum-ion units may carry a $1,500 premium, offset by fast charging capability, while sodium-ion packs aim for entry-level accessibility, emphasizing predictable winter performance over peak acceleration. Moreover, mass adoption of non-lithium chemistries has broader implications for raw material markets. Reduced reliance on lithium and cobalt could ease price pressures for legacy lithium-ion vehicles, while also mitigating geopolitical risk associated with concentrated lithium supply chains. Aluminum and sodium are abundant and geographically distributed, which could, over time, allow Tesla to scale aggressively without bottlenecks that have hampered other manufacturers. Analysts estimate that by 2028, non-lithium packs could account for 25 to 30% of Tesla's global EV output, with a particular impact on entry-level and senior-focused segments. Finally, the 2026 rollout may serve as a litmus test for Tesla's long-term energy strategy. Success with aluminum-ion could validate ultra-fast charging in mainstream EVs, potentially influencing supercharger network upgrades to support 200 to 250 kilowatts peak power. Success with sodium-ion could set new standards for cold weather reliability, potentially inspiring a wave of sodium-based pack adoption across Asia and Europe. For senior drivers, these developments translate into tangible benefits: less anxiety about range, faster mid-trip charging, and vehicles designed for longevity, not just headline performance. So, which chemistry would fit your driving style? Comment aluminum or sodium to let us know. Share your thoughts in the comments. We're curious to see which direction you'd take. Over the past year, China's major players, GAC, CAC, Chery, Sunwoda, BYD, and even the usually cautious CATL, have all accelerated their solid-state programs. GAC now leads with an active production line making 60 A+ cells, while CAC targets even larger 75A units for long-range EVs. Chery is aiming for a 600 watt-hour per kilogram module, the highest target in the group, and CATL maintains that true large-scale commercialization won't arrive until around 2030. To put that shift in perspective, today's lithium-ion cells sit at roughly 20 to 40 ampere-hours. Jumping to 60 to 75 ampere-hours, paired with near double energy density, heat tolerance above 300 degrees Celsius, and non-flammable solid electrolytes, unlocks what automakers have promised for years: safer packs and real 1,000-kilometer EVs on a single charge. And this global shift matters for one reason: Tesla is not sitting still. The company is now working on its own solid-state program intended for the upcoming Model 2 platform. With competitors preparing mass production between 2026 and 2028, Tesla's compact EV will need a next-generation battery system if it hopes to maintain its lead in affordability, range, and long-term durability. So, we're here to break down that new solid-state battery tech in today's video. Where does Tesla stand as solid-state production lines finally go live? For the first time in over a decade of battery innovation, Tesla is facing a genuine shift in the competitive landscape. With Chinese manufacturers activating 60Ah to 75Ah solid-state pilot lines, the pressure is no longer theoretical, it's industrial. And this is exactly why insiders say Tesla has accelerated its own solid-state program, aiming to deploy the chemistry first on the high-volume Model 2 platform. While GAC and CAC are proving that large-format solid-state cells can move beyond the 20 to 40 ampere-hour norm, Tesla is taking a different angle. Instead of rushing a prototype to market, the company is focusing on manufacturability, cycle stability, and vehicle-level integration, areas where Tesla has historically pulled ahead once the real scaling begins. According to multiple engineering sources, Tesla's internal target sits in the same 60 to 75 ampere-hour window, but with a stronger emphasis on thermal robustness, fast charge tolerance, and low-cost electrode processing, similar to the dry coat strategy used on the 4680 line. How is Tesla's solid-state battery actually different from other EV cells? Tesla's solid-state program represents a major departure from traditional EV batteries, and even from the early solid-state prototypes emerging from China. Rather than relying on a simple ceramic electrolyte pouch that performs well only under controlled lab conditions, Tesla is engineering a multi-layer oxide solid electrolyte designed for high-power EV applications and mass production at gigafactory scale on the existing 4680 line. At the heart of Tesla's design is a hybrid anode structure, combining a high lithiation silicon scaffold with a thin lithium metal layer that forms during the first charge cycle. This configuration reduces volumetric swelling by up to 60% compared with pure lithium metal anodes, and allows the theoretical gravimetric energy density to reach 550 to 620 watt-hours per kilogram, a figure nearly double the standard lithium-ion cells currently deployed in Tesla's Model 3 and Model Y, which typically range between 250 to 300 watt-hours per kilogram. The solid electrolyte itself is a laminated multi-phase stack rather than a single brittle sheet. The top layer is a fast-ion conducting oxide, achieving ionic conductivity of 5 to 10 millisiemens per centimeter, enabling high current discharge without overheating. Beneath this lies an elastic polymer interface that absorbs mechanical stress and stabilizes the lithium metal surface during repeated cycling. The final layer is a reinforced ceramic barrier, providing both puncture resistance and thermal insulation. Combined, this structure allows each cell to maintain stability under nail penetration tests, short circuits, or localized heating above 300 degrees Celsius, conditions that would cause catastrophic failure in conventional lithium-ion packs. What makes Tesla's approach especially disruptive is its manufacturing-first strategy. Instead of developing an entirely new form factor or specialized tooling like Toyota or Solid Power, Tesla has engineered these solid-state layers to integrate directly into the existing 4680 production line. The dry electrode coating process remains compatible with the new chemistry, and the laminated solid electrolyte can be roll-pressed in a manner similar to traditional separators. This approach preserves the mechanical and thermal advantages of the 4680 casing while reducing capital expenditure by an estimated 40 to 60%, compared with building a completely new production facility. Tesla's internal performance targets demonstrate the potential of this technology. The company is aiming for cell-level energy densities above 500 watt-hours per kilogram, volumetric densities exceeding 1,000 watt-hours per liter, and real-world ranges over 1,000 kilometers, 620 miles per charge. Fast charging is also a priority, with a 10 to 80% charge in roughly 10 minutes projected under high-power DC conditions. Additionally, the design anticipates 1,500 to 1,600 full cycles before dropping 20% of its capacity, meaning the pack could last over 1.6 million kilometers, effectively covering the lifetime of multiple vehicles. Combined with extreme thermal stability and non-flammable electrolytes, Tesla's solid-state packs are designed to deliver unprecedented safety, longevity, and energy performance, forming the foundation for the company's next-generation crash-proof EV battery. What can Tesla's solid-state battery really deliver in the Model 2? While Tesla's solid-state cells have demonstrated impressive performance in lab testing, over 1,000 kilometers of range, 10-minute 10 to 80% fast charging, and 1,500 plus full cycles before 20% capacity loss, the real-world application in the Model 2 will inevitably introduce some differences. Vehicle integration, thermal management constraints, and weight distribution all affect final performance. Experts estimate that the Model 2 will achieve around 900 to 950 kilometers of range per charge, slightly below lab projections, but still nearly double the range of current compact EVs with standard 20 to 40 Ah lithium-ion packs. Charging performance also adapts in real conditions. While lab cells reach 10 to 80% in roughly 10 minutes under ideal cooling and power delivery, the Model 2's pack will likely achieve 10 to 80% charge in 12 to 13 minutes at compatible high-power DC stations, accounting for voltage drops, pack heating, and power electronics limits. This is still far faster than conventional lithium-ion systems and makes long-distance travel practical without extended stops. Durability sees a similar adjustment. Prototype cells endure 1,500 to 1,600 cycles to 80% capacity in controlled conditions. But real-world driving, characterized by variable temperatures, irregular charge patterns, and repeated high-power discharges, suggests the Model 2 solid-state pack will sustain roughly 1,200 to 1,300 cycles before reaching 80% capacity for an average driver. That still corresponds to over 1.2 million kilometers, effectively covering the vehicle's entire operational life. Safety and thermal management remain strong differentiators. Even with minor efficiency losses in the pack system, the laminated multi-phase solid electrolyte is expected to maintain stability above 280 to 300 degrees Celsius, keeping risks of thermal runaway or electrolyte ejection negligible under real-world stress, including fast charging, high-speed driving, and extreme weather. How is production and launch timeline for solid-state cells? Tesla's solid-state battery program is moving from the lab toward industrial-scale deployment in a highly methodical way, prioritizing both reliability and manufacturability. According to internal sources, the company plans to begin small-batch pilot production in 2026, leveraging modified 4680 lines at its existing gigafactories. These pilot runs will produce limited quantities of 60 to 75 amp-hour cells to validate assembly, integration into modules, and real-world thermal performance. Each batch will undergo rigorous vehicle-level testing in prototype Model 2 units, ensuring that the cells meet Tesla's demanding safety and performance standards before ramping up. Full-scale production is expected to follow between 2027 and 2028, coinciding with the scheduled launch of the mass-market Model 2. By integrating the solid-state layers into existing 4680 manufacturing lines, Tesla avoids the massive capital expenditures associated with building an entirely new production facility, while ensuring consistent quality control across thousands of modules. Industry analysts estimate that Tesla will initially produce tens of thousands of packs per year, scaling to hundreds of thousands annually by 2029, depending on supply chain availability of high-purity lithium, silicon, and oxide electrolytes. The timeline also accounts for vehicle-level rollout milestones. Early Model 2 prototypes equipped with solid-state packs will undergo extensive road testing in multiple climates, including extreme heat and cold, to validate the thermal stability and durability projections made in lab conditions. Real-world range, charging efficiency, and safety metrics from these tests will inform final production specifications. Tesla is reportedly targeting a public reveal and limited customer deliveries in late 2027, with broader market availability in 2028, once production volumes reach a commercially sustainable level. While lab numbers are impressive, real-world deployment will ultimately show how well Tesla can translate this breakthrough into everyday driving. What excites you most about Tesla's solid-state technology? Range, charging speed, or safety? Do you think the Model 2 will finally make long-distance driving effortless for compact EV owners? How soon would you consider switching to a solid-state Tesla if it hits the market?
Can have an EV and make it through the winter, without serious issue. I think that should be the gold star that we're all pointed toward as we think about moving toward more EVs across the country.
Are you struggling with your EV this winter? Are you hoping for new solutions that can finally fix those cold weather problems?
Scientific solutions is already existing. It takes time for the auto industry to implement practical solutions and start to provide viable product to our customer.
1. How can solid-state batteries blow away winter problems? What's inside? First, traditional lithium-ion batteries rely on a liquid electrolyte that facilitates the movement of lithium ions between the anode and cathode. However, this liquid electrolyte thickens in cold weather, reducing ion mobility and decreasing the overall efficiency of the battery. This forces EV users to take longer charging times and take reduced range since the energy is lost faster during winter months.
You can tell the battery does go out faster.
It's complicated because, I have to take time out of my day, sometimes every other day just to charge and, refill my battery.
In contrast, solid-state batteries utilize a solid ceramic or polymer electrolyte that remains stable and efficient even at negative 30 degrees Celsius. The solid electrolyte allows ions to move freely without resistance, ensuring that the battery maintains its performance levels regardless of the outside temperature. This means your vehicle is charging faster and has less range drops when using solid-state battery. We will discuss this later in this video, but what is truly different is the use of advanced materials tailored for cold climates from Tesla. Unlike traditional batteries, which rely on graphite anodes that can suffer in freezing conditions, Tesla uses silicon or lithium metal anodes. These materials not only reach faster energy transfer, but also offer higher thermal stability. In practical terms, this means your Tesla EV can accelerate from 0 to 60 miles per hour in the snow just 0.2 seconds slower than under perfect conditions. Moreover, power loss is minimized to a mere 3 to 5%, compared to the 15 to 30% losses of lithium-ion batteries in similar conditions. In the cold season, what problems are you having with your EV? If your vehicle cannot accelerate fast, please drop a 1. And if your vehicle loses power quickly, please drop 2. If not, please share with us in the comments section below. Come back to the solid electrolyte. It acts as a thermal insulator, preventing cold from penetrating into the battery's core. This maintains a stable internal environment, critical for consistent performance. Even after a night in negative 20 degrees Celsius, a solid-state battery can help your vehicle retain 95% of its charge, while a lithium-ion counterpart would see a significant drop of 60 to 70%. This reliability means that you don't have to worry more about range and acceleration on frosty mornings. 2. How do solid-state batteries offer higher performance even in snowy conditions? One of the biggest issues for EVs in winter is slow charging. If temperatures drop below freezing, charging speeds can be reduced by 30 to 50% due to the thickening of the liquid electrolyte inside traditional lithium-ion batteries. That's why Tesla's current 4680 battery can take up to 40% longer to charge in the winter, which means you have to wait up to 45 minutes at a supercharger just to get enough charge to continue your trip. Moreover, using a solid ceramic or polymer electrolyte that maintains high efficiency, even at negative 30 degrees Celsius, Tesla's new solid-state battery can charge as fast as it does in warm weather. This battery also eliminates the risk of lithium plating. This is a dangerous issue that occurs when charging a cold lithium-ion battery too quickly. In this case, it damages battery cells permanently and forces EV makers to limit charge speeds in winter to prevent long-term degradation. Now, users can charge at full speed in freezing temperatures without harming the battery. Another problem of EVs during this season is energy waste. In reality, the battery needs to preheat itself before charging or delivering full power, which wastes 5 to 8 kilowatt per hour of energy just warming up. However, Tesla's new solid-state battery solves this problem with a built-in self-heating mechanism that activates whenever the battery is charging or discharging. Instead of using extra energy to warm up, the battery heats itself naturally as it operates, reducing preconditioning energy waste by 80 to 90%. So now, you don't waste your energy as much as before, even before you start your EV's motor. In an easy grab, using solid-state batteries helps your vehicle operate more stably in cold conditions. We are referring to reliability and safety when traveling on freezing highways, for instance. In places like New York, where winter storms can leave you stuck in the roads for hours, or in Los Angeles, where unexpected temperature drops can catch you off guard. You will be more comfortable since your EV now has faster charging rates, higher energy efficiency, stable range, or higher accelerations. It's such a big difference between driving to your home safely or needing to find an emergency charging station in freezing conditions. 3. How and how long does a solid-state battery heat your car? One of the biggest concerns for EV owners in winter is keeping the cabin warm without running out of battery. IAA researchers have discovered that controlling cabin temperature can consume a substantial amount of power because batteries don't function as well in cold weather. Unlike traditional EV batteries that rely on inefficient liquid electrolytes, Tesla's solid-state battery has higher thermal conductivity, This means that when heating the cabin, less energy is lost, allowing the car to reach a comfortable temperature much faster while consuming far less power. So what Tesla model are you using? Are your vehicles struggling with heating problems in this season? We're glad to hear about your sharings. Now let's see how much time you have to spend heating your cabin. Take a Model Y in extreme winter conditions, for example. With a traditional lithium-ion battery, warming up the cabin from negative 20 degrees Celsius to 20 degrees Celsius can take 15 to 20 minutes, and a significant portion of the battery's power is wasted in the process. But with the solid-state battery's 95% heating efficiency, the same process takes only 6 to 8 minutes, which shows a 60% reduction in heating time. If you are using the Model S Plaid, instead of waiting 12 to 15 minutes, now you can enjoy a fully warmed cabin in just 5 to 7 minutes. And if you own a Cybertruck, you have to take just 10 minutes to fully heat the cabin, compared to 20 to 25 minutes with a standard lithium-ion battery. And how does the battery heat your cabin? It uses a heat pump system that draws power directly from the battery. This system also absorbs heat from the surrounding environment, even in sub-zero temperatures, and efficiently redistributes it inside the cabin. Thanks to this, energy consumption is low by 30 to 40%. By contrast, traditional lithium-ion battery systems use resistive heating, which works by converting electricity directly into heat. While this method is effective, it is also extremely inefficient, draining the battery rapidly and significantly reducing driving range. This causes a range drop by 20 to 30% in freezing conditions. If a Model Y is equipped with a standard lithium-ion battery, heating the cabin from negative 20 degrees Celsius to a comfortable 20 degrees Celsius could consume up to 8 kilowatt-hours of energy, reducing driving range by nearly 30 miles per hour of heating. But with the solid-state battery-powered heat pump, energy consumption is just 5 kilowatt-hour, which can gain nearly 10 to 15 miles of range per hour. That means you stay just as warm while keeping more energy for the road. But is this heating process safe? Yes, you don't have to worry about this issue. Unlike gas-powered vehicles, where carbon monoxide poisoning is a major risk, Tesla's EVs do not rely on combustion, which eliminates that danger. Next, Tesla uses sensors in their vehicles to detect any movement inside the cabin, ensuring that if conditions become unsafe, the system alerts you immediately via the Tesla app. Moreover, a solid-state battery also allows the cabin to maintain a steady temperature for longer, meaning you can confidently leave your child or pet in the car for short periods without worrying about extreme heat or cold. Let's find what happens when your Tesla sits overnight in freezing temperatures. If left outside for 8 hours in negative 20 degrees Celsius, a traditional lithium-ion battery would allow the cabin temperature to drop to 5 degrees Celsius, requiring the heater to restart. But with a solid-state battery, the cabin maintains 15 degrees Celsius naturally. In even harsher conditions, after 12 hours in negative 30 degrees Celsius, a traditional lithium-ion battery would need a full preconditioning cycle of 30 to 60 minutes before reaching optimal temperature. Tesla's solid-state battery, on the other hand, requires only 5 to 10 minutes to warm up the cabin. This means even when you leave your vehicle in the parking side after a cold night, you can start driving almost immediately, rather than waiting nearly 1 hour for the battery and cabin to warm up. Are you ready to use a solid-state battery for your vehicle? Are there any other features do you want Tesla to update with this solid battery? Or what do you want Tesla to improve in their current 4680 battery? We are eager to get your insights. And that wraps up the biggest battery shakeup Elon has ever positioned for 2026. Aluminum ion for insane power density, sodium ion for cost-crushing scalability, and solid state for long-term durability. 3 technologies lining up to redefine every Tesla product from the Model 2 to the next-gen energy storage. If you found this deep dive helpful, hit like, drop a comment, and subscribe, because the next video is where we break down how these batteries could kill today's lithium-ion market faster than anyone expects. Thanks for watching, and I'll see you in the next one.